This session is on cloud-based computing. Our first speaker is Andreas Bayer, who is a research scientist at NEC Labs Heidelberg. So without further ado.
Thanks a lot. Yeah, I'll introduce you to our. Shall we start, or we'll wait for another minute? Okay. Yeah, it's the dynamic resource allocation for cloud-based media processing. So we deal with some DB-like cloud-based video processing system that delivers streams to smartphones, browsers, to HTML5 capable devices. That's kind of the motivation to start with a resource allocation in the first place. I will introduce this system shortly, so you know where the tasks are coming from we need to handle. We claim that our solution is pretty generic when it comes to media tasks, but yeah, at the end, it only sticks to media tasks because of their characteristics. We will talk about the resource allocation approach, how we leverage the survival function and machine learning to increase the accuracy of our prediction. I will show some result measurements we've done and give an outlook on what's to be done in the future from our side. So the media pass system itself is, as I already said, delivering TV-like live video streams to mobile devices and browsers. We heard in earlier sessions, and I think also in the keynote, that it's quite difficult to bring content which is in one specific codec or format to a variety of devices, because you either need to adapt to their display resolutions and aspect ratio, or you have to install a plugin to handle the incoming streams. That's not always possible, since, for example, iPhones are quite restrictive in what they allow you to install and what not. So therefore, we decided to create a system which serves the video tag. That by browser vendor, you have specific requirements, so only a subset of codecs is accepted, and the system therefore takes care that a live transcoding of your content happens, and then you should be able to switch channels and do basically the same stuff you know from your set-top boxes in the living room, but just without the set-top box, which would be great, because then no one needs to maintain the set-top box, which is getting fairly complicated as they are getting more complex. So we see this system, it's basically communication connection layer. All the video processing is done by GStreamer pipelines, and this end-to-end pipeline from seeing the content in the first place and delivering the output transcoded content to the device. This is split in several tasks which we deploy in the cloud. Simple reason is that if you set up an end-to-end pipeline, it's quite static, you cannot manipulate it anymore, and we want to be able to scale in choices or in connected devices. So if a second person decides, or a second group of person decides to consume the very same content some other person consumes on an iPhone with their Internet Explorer or something, we want to leverage some of the computations. We don't want to reuse what we already did. Since it's live content, everyone is basically expecting the same stuff, so why not giving them exactly the same output? We will see. Okay, these parts I do not describe here because it's too focused on the media pass aspect, recognizing the client device and coming up with the initial pipeline to produce content for it. I just want to motivate the task set we generate, which is then handled by the resource allocation to be mapped on our cloud machines. So the upper example shows you the end-to-end pipeline. You read a certain source. This might be transport stream or something. You have to demultiplex it. You decode, eventually edit it by user choices. You encode it in a codec that is understood by the client device, so the destination browser. This might be a VP8 and VP8 video, Vorbis audio for targeting Chrome device. You have to provide MP4 in the HLS format to target IE devices in general. So these tasks are represented as the pink boxes here. This is the most CPU-intensive phase of the transcoding, and then we multiplex the audio and video choices to stream them out in the appropriate container format. As the boxes indicate, this end-to-end pipeline was split by the basic tasks they do, like demultiplexing, decoding, editing, encoding, and multiplexing the content. And this then maps to this little colored bubbles down here, which represent the processes generated by us. So depending on the user requests which come in from the browser, these bubbles occur or disappear in the cloud system. And as the pipeline is not continuous anymore, but chunked in little pieces, we can dynamically interconnect them and spawn additional producers, kill those which are not needed anymore because the last user using a Chrome browser turned off. And yeah, that's the tasks we are dealing with in the rest of the presentation. Yeah, this relates to kind of bin packing problems. So this is how we started to investigate this deployment on virtual machines, because for us, of course, minimizing the CPU utilization of those tasks is the intended outcome. But for someone deploying such a system, the important question is, how many VMs do I have to buy from Amazon? How many virtual machines do I need to spawn to finish my task? And so we have to find a balance between a minimal set of virtual machines able to compute whatever is requested currently, and a maximum user experience, because that happens when we do not properly allocate the resources. If these tasks overutilize the CPU, frame drops occur, and your output just does not look as nice as it should, or you have strange sound.
Did you say minimizing CPU utilization?
Yeah.
Do you mean this? Minimizing CPU utilization.
Okay,
that
maximizing.
means to use
Okay, we.
as bad as possible. Is this your?
That's
approach?
clearly not what we are up to. You're right. Thank you. So we want to use as few virtual machines as possible to achieve our task. Okay. Breaking our continuous pipeline in little chunks means that we have several little media processors, and we inspected their behavior, how they utilize the CPU, and it turned out the consumption follows normal distribution. So we can say that there's a certain mean utilization of the CPU we expect a given configuration to consume, with some variance in distribution. This histogram is, okay, it's easy to explain. These encoders and decoders, which are the heaviest tasks in, the encoders are the heaviest tasks in the system. They work on a frame-by-frame basis, and basically the operations done on these frames are reoccurring and only depend on the complexity of the incoming content, depending if you have a still frame or a high dynamic, let's say, soccer game or something, which might pose a bit more effort on the encoder. So these are the distributions of our scripts, which are normally distributed. And another characteristic of our tasks is that compared to, let's say, a web server or something, you might want to deploy in a cloud-based manner, we noticed they have a fairly small variance. So given the high mean values of the encoding task, it varies a little, while with a web server, for example, you might experience certain peaks in the CPU utilization depending on the incoming requests, which are not continuous at all. They're randomized. With this assumption that we have a high mean and a small variance, we can now start looking into how we stack many of those processes on a virtual machine or a set of virtual machines by obeying a threshold, so avoiding the overutilization of the given CPU. That's basically what we expect from our resource allocation algorithm. We want to map a set of tasks to a set of resources, in our case the partial GStreamer pipelines, to a set of virtual machines Typically, you want to monitor and allocate the CPU usage, network bandwidth, and memory. Our example focuses on the CPU usage because we noticed that memory is not a big deal. So it's a problem which you solve on a certain virtual machine. It's the same problem for each virtual machine, and monitoring revealed that memory is not consumed by those kind of tasks, at least not in a noticeable amount. And honestly, our setup is too small to run in network trouble. So that's something which you will see again in future work and which we have to deal with, but currently is kind of ignored because it doesn't pose a problem. These restrictions that might apply, they come from the nature of the task we are dealing with. In live content, you cannot postpone some processing in order to optimize your layout. You also cannot interrupt your processes in the middle because you have a client or a set of clients at the end which expect continuous output. It means you have to continuously keep the processing running and keep the delays or latencies quite small. That affects all buffers in the system, but it's nothing which has to do with the resource allocation. The decision making, that's also kind of optional and does not need to be dealt with in resource allocation. You might have the freedom to choose the order of computation or interrupt your processing. That's again something for future work, task migration, to optimize the layout, which basically gives you, after some tasks disappear over time, the opportunity to aggregate your, like a defragmentation, aggregate your layout. But we will focus on the CPU distribution, and therefore followed two approaches. The first one was to implement a static resource allocation algorithm that basically has a database of historic measurements, typically done within the second, so each second a single process runs. From there we would calculate a mean value and then start adding up tasks until this mean value for the given virtual machine is reached. That's good approach if it works, if your variances are small or your thresholds are so relaxed that you fill your machines for like 70%, and then you automatically deal with the variations because you will never hit the 100%. If you want to utilize more from your CPU, like the 90% level or something, for this we had to go to a dynamic resource allocation algorithm, which means that we now also took the variance into account. The dynamic resource allocation is not calculating a certain mean from known processes in our database, but rather builds a model, machine learning, which we take as a black box. We feed it with the computations and measurements in the database, and generate a model which tells us the variance and mean value of the expected consumption a new task might have. So if we are generating a pipeline which never run before, but is quite similar to pipelines which were deployed in the system, then this helps us to estimate what the resources would be this task consumes. Of course, now we need to monitor our VMs to know what's happening there, to do accurate measurements. We need to monitor our tasks to have a task level basis on network utilization and CPU utilization. And how we solve this is in the following. So we will have a comparison of both later on. But first, for the principle of stacking up those tasks, each of these media processing tasks follows the normal distribution, and if you combine those normal distributions in their mean and variance, you of course, as a result, you have a new normal distribution for which you then have to decide if this combination of tasks can be deployed in a certain virtual machine, or if you may even be possible to add a fourth task to it and then deploy the fourth task on a VM which is already running 3 pipelines. These are the limits we have to take care of. And to solve this, we use a Q function or a survival function, which tells us the likelihood that a certain setup with given overall mean values and variance values will fail or will succeed in being deployed in the virtual machine. Failure is basically a frame drop, so it's not the end of the world, but still that's what we want to avoid. It's now the single-dimensional bin packing problem. It would be multi-dimensional if we take network in account. This will eventually happen in the future. And as stated before, memory is none of our concern. So this Q function that takes the variance and the mean and computes a certain, for a certain Q level of confidence, we can then make decisions of combinations of mean and variance if they obey our threshold or not with a certain percentage. So basically, we typically choose like 1% chance to hit the 90% barrier in CPU utilization, and this avoids frame drops very well. This is the same as a formula. If you take we compute the probability that the actual resource utilization exceeds this maximum utilization we defined before, and yeah, we compute this by combining the total mean values, the mean values of the single tasks, so total mean, and calculating the total variation from the single variations of tasks. And of course, monitoring has to happen per VM, as our system should scale. We do not have like a central mastermind knowing everything. Each time we spawn a VM, there's some analytics client running on it, which monitors the single tasks that register to it, basically which are deployed to this system. This will keep track of CPU utilization and the network traffic, inbound, outbound, and report those to an analytics server and writes it in a central database. There we fetch data and compute a machine learning model from it, which we afterwards can query whenever a task has to be deployed to the cloud. So from there, the information comes what's the expected mean and variance to a unknown or known, doesn't matter, configuration of pipeline setup. Yeah. The model of the overall architecture looks like this. We have the cloud, where we have our worker machines. There we initialize machines and set up this analytics script in the first place. From there we get data reportings from all tasks which are deployed so far. These are aggregated in the model and sent to a classifier that's especially for the static algorithm needed to divide the single kinds of tasks, because you cannot calculate as a mean for every task. We are deploying these splitters, producers, consumers. The producers might have audio or video configuration, which significantly changes their CPU utilization. So the classifier tells us in which category a certain task set falls and helps to compute the mean for a given set of tasks. This is then also basis for the parameters which specify our pipelines. As I said, it's basically a GStreamer configuration on the task that needs to be processed in the future. This we give to the inserter that sets it to the appropriate machine, and that makes use of the model which was generated before to judge if it fits a machine or not. In addition to this, we keep a bunch of Slack machines. These are resources where we can deploy tasks that do not fit the current setup of machines. It's just helping us in speeding up the deployment process, because users might expect their channel switch to be executed rather sooner than later. So we do not want to wait for a new VM to boot, in addition to initializing all the copying of initial scripts and everything. So these machines are kind of pre-configured and ready to deal with tasks that don't suit the actual workers, and therefore the Slack machine would move in the worker pool, and we would have to spawn a new Slack machine or two, or whatever is the size of our deployment. So this Slack controller also knows how much space is left on all worker machines together, so how many tasks we would be able to deploy in the near future. If this is too much space, then we can save the machine and turn it off. This minimizes our VM utilization. And if the Slack controller encounters that the worker machines are almost loaded to 90% CPU utilization per machine, then it would spawn new Slack machines to be able to react on incoming requests. So the responsibilities of this system, as a summary, are building the model from the historic data and monitor the tasks which are running. The measurements are also fed in the database, and if enough new measurements are available, then we will recompute our model to have a more accurate prediction in the future. This might happen on the fly during the run. We have to check these Slack machines, so we call them, so the spare machines, and of course do all the task submission related stuff like receiving the request to deploy something, judging the weight of the task, and submitting it to a suitable virtual machine. The estimation our system generates looks like this straight line. That's not really the truth, as you can see. These up and down lines. This is the current measurement which is done, but yeah, it's good enough to do estimations, and this basically shows the mean value of predicted utilization. It comes with a little variance which we are not painted in this picture. And you see that there's a certain difference between measuring the tasks we deploy and measuring the overall CPU, because a little overhead is produced by the operating system of the virtual machine itself or by the OpenStack environment. So there's always a little difference between them, which means setting the CPU level to 100% will never succeed, because like 4 or 5% are always occupied by the VM operating system itself. This would be the comparison of our static resource allocation and the dynamic resource allocation. We here have shown the number of pipelines we are running. This corresponds to number of channels we are offering, like running BBC and CNN. So 8 of these channels were running. Up to 8 of these channels were running, and here you see the number of virtual machines we needed to fulfill these tasks. So of course in the beginning there's not a big difference between just calculating the mean value and taking the variance into account, but as you can see, with more and more channels it is significantly better to use the dynamic resource allocation, which in this case saves us like 1 VM, and yeah, so it's good to do so. This is the efficiency of dynamic resource allocation. We have compared several confidence levels. That means always always obeying this 90% barrier with a very strong confidence level is indicated in the first bars. And you see that for 8 pipelines you would need like 7 point something, so at the end 8 machines. And on the other end, a rather relaxed algorithm that every now and then allows you to obey or to overutilize our CPU. That saves in this case up to 2 machines, and as I said, it's not like overutilizing the CPU kills the system. It's basically a frame drop for the user, which at the end we cannot avoid, because there's transport in between. There is the decoding device itself, which the user uses. So we do not have control over the full delivery pipeline. We just can take care that in the content we are streaming to the client are not already frame drops encoded, so to say. The effectiveness of the dynamic resource allocation is shown here. So this is not the static versus dynamic. This is dynamic with the 0.4 confidence against the 0.1. So the chance to hit this barrier was a bit higher in the dotted line, and therefore it uses one machine less for the same set of pipelines roundabout. It just says that now you have a parameter to control the quality of service you deliver and the amount of resources you use. So for clients, it's sometimes interesting to have a kind of gold membership they can sell to their customers. This would mean to have a guaranteed frame drop free delivery, at least from the cloud system. And the others you can have serve with a spare capacity, if you want to say so. For the future work, we would like to deal with the multi-dimensional bin packing problem, as we have solved it for CPUs. We would like to include the network traffic, especially when the deployment gets a bit bigger than, I think, currently 3 plate servers building our cloud. Memory we do not intend to deal with, because even in huge deployments, the virtual machines memory would perfectly fit the requirements. Optimizing the current layout is always a big issue, and as I said, task migration might help, because from the, shall I show the first slide again, second slide? There was this picture with the bubbles. So task migration could help, because if someone disconnects on this side the associated producers, if this was the last client using the producer, might die and be removed from the system. Therefore, we have new capacities on one server, and currently we would only deal with those new capacities if a new request arrives in the system. So we have a brand new task to be deployed. If we could compact our setup on the fly, that would probably help a lot in terms of utilization. What else was in the future work slide? Slow computer. Okay. Spawn different virtual machines. This bin packing problem in general assumes that you have set of bins which are homogeneous, and you put a set of tasks in them and you try to solve this problem. Solving it in a multi-dimensional way, but also taking the traffic consumption of the tasks into account, which is at the end the more severe implication. Hitting the CPU barrier means a frame drop. Hitting the network barrier means not being able to stream out the entire output you compute. So this would be very interesting to solve, and the heterogeneous cloud that helps us also in saving bandwidth in a way, because with every virtual machine you spawn, you assign a certain set of CPUs from the host to this machine, and in addition this machine is then equipped with a virtualized network card. So if you know that your processes in the machine will use lots of computation, and then at the end come up with 1 or 2 streams which are 3 megabits each, it's enough to have one of these virtual network cards. It would make no sense to have such a huge machine with 8 cores or something, a virtual machine, deploy lots of tasks on them, tiny tasks, which in combination exceed the limits of the virtualized network controller. So this would help us to deal with HD video streams, or hopefully the 4K video streams, but I'm not sure if we can do this in a single host machine, because already virtual machines with 6 cores are needed to process a HD video in real time. But that would be the future work on heterogeneous setups. We could show that manually creating those setups by just adding a machine with a different templates or a different set of CPUs to the system is handled well by the resource allocation, but the decision making to spawn such a different machine in the first place, this is what we would like to investigate, and to know when it's worth doing this and when the standard dual cores or whatever do the job. So, as a summary, This was our media pass application, spawning tasks, delivering TV content. We've seen the dynamic resource allocation, which deploys those tasks, monitors them, and updates a machine learning model to be able to deal with future tasks, which are alike but slightly different from the ones which are already there. In addition, we need to keep track of our virtual machine installations in total and take care that we have not too many virtual machines, but enough to compute them. That's it.
I have a clarifying question. Ayman Arbat from Qatar University. So the question is, do you consider a private cloud or a public cloud like Amazon, where you are sharing with people you don't know about and maybe you have interference across VMs?
Currently, the system is deployed in a private cloud in our lab. From API and compatibility, it should not be a problem to deploy it as a public cloud in Amazon. Of course, it would still be a kind of closed environment, so we do not intend to give anyone access to the real implementations or the internals of the virtual machine. That should be shielded, but the functionality that a client connects to a front end and the front end communicates to a management unit what to set up and where to pick the output for the client, that would be the barrier to the public part.
Yeah, I'm just concerned about using history, and would history make sense in the context of a public cloud? Like you might be a multi-tenant with another application that's demanding, or you might be sharing the machine with other people, so the interference part is what I'm thinking.
Yeah, that's true. We would rely on exclusively using the resource. So there's no multitasking and swapping out and in machines in this approach. That's true.
One last question. Hold on.
From your second slide, or next probably, yeah. So there's an impression that you use this transcoding in the cloud. And what kind of library do you use? I mean, this FFmpeg or this kind of libraries in case of this transcoding?
These pink boxes doing the transcoding?
Yeah.
These are GStreamer pipelines we configure to decode incoming, I don't know, MPEG-2 video transport codec and encoding it to, let's say, VP8 or Theora.
Okay. Then this from this FFmpeg libraries, as far as I know, that they use it when they're transcoding. They use this multi-threading or this kind of things. So in case of this resource access, so when you have this multi-core processes, so these threads are, I mean, these shared among different kind of CPUs, different CPUs. So does this virtual machine can also allocate this kind of cores in kind of this threading allocation?
Yes, there's definitely a difference between setting up this task to use a dual-core processor or 6 or 8 cores. So you can define the multiplicity when configuring the encoder. So
Okay.
based on the virtual machine template we chose, if we spawn a dual-core or a quad-core or a 6-core, we would adjust the encoders according to the resources we offer.